Hello students, today we will derive an expression for path difference in thin films due to transmitted light. So let us begin first with the diagram. Now this is the case of thin film in transmitted light. So let us take a thin film of thickness T, refractive index mu. What are the necessary conditions for fringe pattern to occur? Monochromatic source, coherent sources and path difference. So let a ray of light be incident from a monochromatic source on this thin film. After getting incident, it will get refracted in the surface and get transmitted out like this. So this is my transmitted ray. Next, inside the film itself, partial light will be reflected and then this will get transmitted out like this. So now here, if my eye is here, I will observe a fringe pattern here because of the interference of these two rays and my coherent sources, this and this. So let us now find an expression for path difference. Let SA be the incident ray, AB be the refracted ray, BC be the reflected ray inside the medium and CD again suffers inside the media. Outside it becomes BP and DQ. Now in order to derive an expression for path difference, we will drop perpendiculars on this diagram. Let us begin. First, this is my first perpendicular. It gives me angle of incidence I. And here my second perpendicular for this triangle, it will give me angle of incidence. It will become I, same because here two parallel lines I have drawn. So this is I and this is I. Next, angle of refraction. If this is R, then we know from maths that two parallel lines, this angle is R, then this angle will also become R. So if this is R, this will also become R. Now ABBC, if this angle is R, this perpendicular has been dropped. They are two similar triangles. Hence, this angle also becomes R. And another perpendicular has been dropped from here. So, once again, this line, if this is R, this will also become R. If this angle is R, this will also become equal to R. And if this is R, from the concept of similar triangles, this is going to become R. Let us draw the perpendicular CM. And one final perpendicular for path difference DN here. This perpendicular. And this angle will be angle of incidence I. Sorry, this one. This will be angle of incidence I. Now we begin to find an expression for path difference. Now path difference will be path travelled inside the media minus path travelled in air. And path difference begins from coherent sources. That means those sources that have been derived from the same source. So, path difference is equal to path travelled BC plus CD inside the media of refractive index mu. We begin from B because it is a coherent source. So, path in film is BC plus CD minus how much has it travelled in air? Here BN, perpendicular which has been dropped. So BN in air. Now our target is to find an expression for BC, CD and BN in terms of I, R, cos, tan, sine. So we will pick up 3 triangles to simplify this expression, and instead of BC, CD and BN, we write them in terms of cosine, sine, tan, etc. to introduce Snell's law in this expression. So we begin with triangle BCM. Triangle BCM. Here cos R, base upon hypotenuse. So cos R is equal to base. What is base? MC upon hypotenuse, that is BC. And exactly what is MC? It is thickness of this thin film. So your BC becomes equal to MC upon cos R. What is MC? It is thickness of the thin film T upon cos R. So now this value of BC which we have found, that is T upon cos R, we will put it here. BC will be replaced by T upon cos R. And if we have a closer look, BC is equal to CD because these two triangles are similar. Hence, this expression will reduce to 2T upon cos R because we are putting T upon cos R. So this gets simplified. Now let us concentrate on BN. For that, we pick up another triangle where we get a simpler expression for BN. Now for solving BN, we take triangle MDC. What is it? MDC, this half. So here cos R becomes equal to MC upon CD, which implies MC is again thickness of the thin film. So CD is equal to T upon cos R. Now next, triangle BND. Where is BND? BND, here, this N. BND. We take sine I. Sine I, that is perpendicular upon hypotenuse. That means BN upon BD. BN upon BD. So it implies BN is equal to BD into sine I. BD into sine I. Let us have a closer look here. BD, that is BD is equal to BM plus MD. So instead of BD here, I can write, BD can be written as equal to BM plus MD and BM plus MD. In order to get an expression for BM and MD, we will take tan of this angle. So it will become all the more simple for us and we can easily introduce Snell's law in this expression. So in this triangle, tan R is equal to BM upon CM. So BM upon CM, and tan R, another way also you can see here, BM becomes equal to CM into tan R. What is CM? Thickness of the thin film. So it is T tan R. Now we can put this values in the expression for path difference. So instead of, and one more thing, BM here, BM is equal to MD. So it is BM and MD. So BN is equal to BM plus MD into sin I. BN is BM plus MD into sin I from this triangle. Straight away, instead of BD, I have written it as BM plus MD. Now, that means, and BM and MD are equal. BM is T tan R. So, T tan R plus T tan R. This expression becomes BN is equal to T tan R plus T tan R T into sin I. So this becomes equal to 2T tan R into sin I. Now from Snell's law, we know that Snell's law is mu is equal to sin I upon sin R. This is Snell's law. So we put Snell's law in this expression and simplify it a bit further. Putting Snell's law here, it becomes B, the path difference from Snell's law, it becomes Bn is equal to 2t sin R upon cos R into sin I. Now, simplifying this expression further, we get, because Bn is 2t tan R, so instead of tan, I have put sin upon cos. We multiply and divide this expression by sin R. Why are we doing this? We are purposely doing it to introduce mu in the expression and use the formula sin square theta plus cos square theta is equal to 1. So now Bn becomes equal to 2t tan R, or you can write 2t sin square, see, sin into this we have multiplied, this is mu, so 2t mu sin into sin square R upon cos R. This is Bn. Putting this value of Bn in the expression for path difference and BC plus CD equal to T upon cos R, which we derived, we finally get an expression for path difference for transmitted light. Now see, BC CD we derived in the beginning is equal to T upon cos R plus T upon cos R minus, what have we derived? Bn as equal to, we have found out Bn is equal to 2 mu T upon cos R into cos square R. So this you can even make it further simple, and this becomes equal to, this is 2 mu T cos R into sin square R, So now 2 mu T upon cos R, take it out common, you are left with 1 minus this has come from T upon cos R. T upon cos R is 2T upon cos R. 1 minus sin square R, and 1 minus sin square theta is equal to cos square theta. So this becomes equal to 2 mu T upon cos R into cos square R. 1 gets cancelled, you are left with 2 mu T cos R. This is an expression for path difference in thin films due to reflected light. 2 mu t cos r. We are not using Stokes' law here because light is getting reflected at the surface of a rarer medium. Hence, no additional path difference here. Quickly, maxima minima for constructive interference, this path difference should be an even multiple of lambda. That means even multiple, that means del is equal to 2n lambda by 2 into 2, that is n lambda for constructive interference. And for destructive interference, del is 2n minus 1. This is minima. This is maxima. 2n minus 1 into lambda by 2, where n is 1, 2, 3. Be careful of that. And del is equal to 2n plus 1 lambda by 2, where n is equal to 0, 1, 2, 3, etc. Now, the very important point here is that for reflected and transmitted light, please recollect that this is the case of transmitted light for maxima and minima. Now, for reflected, it was just the opposite of what you have got here. For reflected, the constructive or maxima one was 2 mu t cos r into 2n plus 1 lambda by 2 and 2 mu t cos r into 2n minus 1 lambda by 2. And here it was maxima, and minima for reflected light was 2 mu t cos r into n lambda. So you can see where the maxima has come for transmitted light, there minima is there for reflected, and where minima has come for transmitted light, there it is maxima in reflected. So they are just opposite of each other. Hence, interference pattern of transmitted and reflected monochromatic light is complementary. Thank you.